chapter 2. So this is the relation of divisibility on the integers. It's a binary relation. You feed in a pair of numbers into it, an ordered pair of numbers, and it gives you a statement, something which is true or false. The statement it gives you is this kind of statement here, B divides A. B divides A. That's how it's read. So that's when I say ordered pair, it means there's a left one and a right one, or a first one and a second one. You know, it makes a difference. You know, B divides A is a different statement to A divides B. It's a statement. It's something which doesn't have a value. Well, it does have a value, but it has a truth value. So there's two possible values for it: true or false. B divides A is true exactly when there exists another integer C, such that you can write A as the multiple of B and C. And it's false when that cannot be done. So when there doesn't exist such a C. And the notation there is that straight line, B divides A. And you can indicate the negation of it by drawing a diagonal line through it, just as you do through the equal sign to denote not equals. So this reads as B does not divide A. Okay? The warning in the box, hopefully people have made this mistake in previous years. If you think about it, yeah, it is a potential mistake to make, is that you mix up the interpretation of that symbol by thinking that it's saying A is dividing into B. When it's written like this, B is typically the smaller one, and it's dividing into the larger one, A, which is on the right. Any questions just about the basic definition? So last time then, we spent the majority of our time looking at the proofs of all the statements in Theorem 2.1. These are a whole collection of basic facts about divisibility. We proved them fully, all of them, by referring back to the definition. Okay? Just by working the definition in various ways, showing the existence of that other integer C or not, as the case may be, we were able to prove all these. Particularly, well, I mean, they're all kind of important, but it turns out we end up referring all the time back to the divisibility of linear combinations. So that is a particularly important one. If we know that A divides B and A divides C, then we also know that A divides any linear combination of B. Okay, so we proved that last time, and that's one that we seem to refer back to all the time. But they're all kind of important, I guess. Any questions or queries about any of those? Or clarification that you'd like? Okay. So once you have the idea of divisibility, you then straight away can define what a prime number is. A prime number, positive integer, strictly bigger than 1, that only has two divisors, namely itself and 1. And we also looked at the statement of the fundamental theorem of arithmetic. If you can think about it, this is now our interim goal in the unit to work up towards that. This says that every integer factors uniquely into primes. They can argue straight away that every integer factors into primes. You just keep factoring it, splitting it into factors as much as you can, and eventually you'll reach a state where none of the small factors you produce can be split any further. That's factoring it into primes. The harder part, the part that does need us to build up some theory, is the uniqueness of it. The fact that you can only write an integer n as a product of prime factors in essentially one way. Okay, trivially, there's a few different ways, because you can just order the mix up the factors in a different order. But really, essentially, if you insist that the primes be in increasing order, then there's one and only one way to express an integer as a product of prime numbers. So it's that uniqueness part that you need to develop some concepts in order to be able to prove. Okay. So about to start the fresh stuff now is 2.3 on common divisors. What we're doing here is we're starting to look at the theory of divisibility, with the view to being able to talk about prime numbers and knowing enough about how divisibility works to be able to prove that uniqueness part. So what we're going to focus on is concept which attaches to a pair of integers, and this is what's known as a common divisor. So if we start off with a pair of integers, a and b, common divisor, c, some other integer, it's kind of defined really just by its name. A common divisor is some other integer that divides into both. So c divides a and c divides b. So any pair of integers a and b can have a whole bunch of common divisors, but there's one that we single out as being particularly important or significant and captures a lot of information, and that's what's called the greatest common divisor. Now, the fact that this exists for any pair of integers comes from the well-orderedness of the integers. Certainly, there is an upper bound on common divisors for any pair because, you know, any integer strictly bigger than the absolute value of a or b won't be able to be a common divisor. Okay, so you can't have a number being a divisor of a number with strictly smaller absolute value. So there is an upper bound on the set of common divisors. And therefore, by the well-orderedness of the integers, there must be a greatest common divisor. Okay, so one of the common divisors that is the greatest. And this is denoted by GCD, AB, greatest common divisor. Some other books, some other authors may refer to it as HCF, highest common factor. Same thing, just a different choice of words. Or you also may come across a define or notation, very compact notation, just simply brackets AB. I'm going to avoid using that notation because it's a bit kind of meaningless and you're only saving 3 letters, and you may as well write down the 3 letters because it's the acronym for the term. So I don't think we're saving much by shrinking the notation down to simply brackets AB. A little bit confusing. So GCD AB is what we're going to call this. So I mean, you know, let's look at some straightforward examples. 30 and 42. This pair, I mean, we can immediately start listing a load of common divisors. Certainly, 1 is a common divisor. 1 divides everything. They're both even. They're both multiples of 3. And of course, the negatives of these are also divisors. However, as I said, when we're studying divisibility, the things you observe with positive numbers are replicated with negative numbers. So we don't normally consider the negative ones as well. We normally just focus our attention on the positive integers. And there's one more, there's 6 as well. But that's basically all of them, or if we include -1 as well. So there are no other integers which are common divisors of this pair, okay, which divide into both. And 6 is singled out as being particularly significant. It's the greatest one. It's kind of significant. And you also notice here that all of the other common divisors, they all divide into 6 as well. That's also something we use. Another example, 75, 45. Yeah. Okay, I'll just focus on the positive ones here. So of course we got 1, we got 5, and 3. Did you say? 15. 15 is the greatest common divisor. Again, we notice, look, it's also the case that all of the other common divisors are divided into 15. Now, one way to understand this, and I may as well give this now, although we're not going to focus on it yet because we don't have the result of the fundamental theorem of arithmetic yet, but we can understand these by looking at the prime factorization. The prime factorization is of 75, it's 3 times 25, so it's 5 squared by 3. And 45 is got a 3 and a 5, 3 times 15. So it's 2 3s and 1 5. You can understand, you know, a common divisor is made up of a product of primes, and it has to be contained in both lists, taking account of the multiplicities as well. Okay. So 5 squared is over here, but 5 squared is not over here. It's under 5. So 5 is the greatest. 5 is 8 common divisor. You got a 3 on both sides, but 9 isn't going to be a common divisor. 9 divides 45, but 9 doesn't divide 7. And so you can kind of think about the greatest common divisor as just the large, is kind of the overlap or the intersection between the two prime factorizations. That is a good way to think about it. That's the correct way to think about it. We're not going to develop the theory of that as yet because we don't yet have, or we haven't formally proved the fundamental theorem of arithmetic. So we just want to, there are some other ways, there are some other computational ways to get at the prime factorizations, sorry, the greatest common divisors. So it all seems nice and simple and straightforward, but you know, you can appreciate there might be problems. You know, so what's the greatest common divisor of this pair? Okay, there's no way of knowing immediately. I mean, one approach would be to take these two large integers and to obtain their prime factorizations, and then just inspect the prime factorizations, find the overlap, and declare that as the greatest common divisor. Of course, we really want to know that the fundamental theorem of arithmetic is true for that to happen. In particular, you know, who's to say that there mightn't be two different ways of expressing this number as a product of primes? Until we prove that there's only one way, and this approach of looking for the intersection in the prime factorizations, that's kind of based on the idea that there is one and only one way of expressing any integer at all as a product of primes. But there is a better and quicker computational way to be able to compute these greatest common divisors, and that's what we're going to work up towards now. But any questions just about the definition, about what we're talking about? It's the GCD of 75 and 40, and GCD of 30 and 42. Okay. Just some other terminology attached to it. In the special case where there are no positive common divisors apart from 1 itself, then we refer to the pair of numbers as being co-prime. Okay? So that's kind of where the two numbers don't share any non-trivial factors at all. So an example of that would be, say, 21 and 25. Okay? If you start looking for common divisors of 21 and 25, you're never going to get any other ones apart from 1 or minus. Okay. So there's only two common divisors at all, and so the greatest of them is 1. This special case we refer to 21 and 25 are co-prime. Well, really we're saying they're a co-prime pair or they're co-prime to one another. So co-prime is again an example of a binary relation, something possessed by a pair of integers. You're kind of not speaking grammatically correct if you say 100 is co-prime. Well, co-prime to what? Could be co-prime to some things, it could be co-prime, not co-prime to them. So co-prime is attached to a pair of things. Okay. So those remarks there are just about wanting to have some way of calculating GCD or articulating it, some way of capturing it without necessarily going straight to the prime factorizations. With the uniqueness. So what we're going to base it on is this important process called integer division with remainder. Again, like a lot of this stuff, it does kind of call back to maybe lots of basic exercises you did in primary school. And really we're just attacking these things in general and building up a theory about them. But like, these kind of statements. When I was in primary school, they had us chanting these things out in unison in order to get them into our heads and be able to do things like this. So what am I trying to write? 100 is 3 times 30, but remainder 10. Okay. This kind of thing. Okay. Taking a large number, identifying some kind of quotient, how many times the smaller number goes into the larger number, and identifying our remainder. Okay. So what we're going to be talking about, and our typical way of thinking about this, of attaching labels to these things, is to talk about performing integer division on the pair A and B, dividing A by B, but just working in integers. So we're never going to say, 100 is whatever 3.33333 times 30, 3 1/3 times 30. We're going to avoid talking about fractions. We're just going to stay in the integer realm. So we're going to talk about some integer quotient. The integer quotient in this example is 3. And then you've got a remainder left behind after the division. Okay? So integer division with remainder is just this process here. Now, what's the theorem saying? Okay, this is an operation you can carry out. The theorem is just putting it on very watertight ground and saying that for any pair A and B, there's a unique pair Q and R. So it's ruling out any kind of ambiguity about the situation. So when you take 100 and you divide it by 30, what the theorem is assuring us is that there is one and only one pair of quotient and remainder such that you can do this. Now, you have to add an extra condition. You have to add some boundaries. So, and the way that's done, because there will be loads of ways to write 100 as something times 30 plus something else. The idea is we want the remainder to be the real, honest-to-goodness remainder. So the remainder is the small number that's left behind after the division. So we insist that this extra bit that you say, it's something 100 is something times 30 plus something else. This something else really is the smallest positive possible remainder. So it's the remainder that has to satisfy this inequality. It has to be a positive quantity. So we can do this integer division with negative numbers. We can accept negative quotients, but we'll always insist that the remainder part is the small positive remainder. So it's non-negative, I should say. It's possible to see a remainder of 0, but we insist that the remainder has got absolute value strictly less than the thing you're dividing by. Because if it wasn't, although we can write 100 as 2 times 30 plus a remainder of 40, well, 40 isn't really the remainder because there is another 30 we can take out and change that to 3 times 30 plus the remainder of 10. Also notice it's perfectly possible to get remainders of 0. That happens when you're dividing it by something that A is divisible by. Then you have a remainder of 0. So again, nothing that someone in primary school wouldn't recognize. But then, okay, so it's easy to, it's kind of easy to appreciate or to feel, to get the intuition that when you divide 100 by 30, there's a unique quotient and a unique small non-negative remainder. But then the question is, what about these gigantic integers, like we featured here in our example? I mean, who's to say there mightn't be something funny going on with large numbers so that you can have a couple of different pairs of quotient Q and remainder R? Well, based on the axioms that we've laid down for the integers, the proof of this theorem rules that out. Okay, so there will always only be one quotient Q and one remainder R. And we'll just talk. I mean, the proof is there in detail. We'll just point out the main parts of it. So the way it works is we construct this set S, and we define this set S to be. We see because the condition, the non-negativity condition, is on the remainder R. The remainder R, you can express that as A minus QB. So we form this set S, which consists of all the possible integers you can hit with the combination A minus TB, where T is playing the role of a general quotient, T is an integer, and we insist that the quantity A minus TB, these are the possible remainders if you like, that they be non-negative. And really, we want this remainder R to be the smallest possible remainder. So we're focusing on the smallest element of S. And we can use the well-ordered axiom, because this is a non-empty set of positive integers, we can use the well-orderedness of the integers to say that, well, if you've got a non-empty set of positive things, somewhere in there is the smallest thing in that set. So S is the set of candidates for the remainder. They're all non-negative. They're all expressed as A minus some multiple of B. And we're focusing on the smallest one. Okay? The smallest one, R. So it's by the well-ordered axiom that that smallest one exists. Okay? So there is a unique R. It's non-negative because by definition everything in S is non-negative. So if R is in S, it's non-negative. The only thing then we have to be sure about is that, well, are we sure that R is strictly less than the absolute value of B? Could it be that some funny arrangement gives you a remainder that's larger than the number B you divided by? Well, that can't happen, and there's just this kind of simple proof by contradiction here. So we're going to claim that R is strictly less than B. So here's a little proof by contradiction inside this proof. So if this were not true, so if R was not strictly less than B, in other words, R is greater than or equal to B, at the same time R has this form, A minus QB, and just kind of like what I did with the example here where I did have a 2 times 30 plus remainder 40, we just go and we take out another B out of the remainder R. So that's what we do here. We subtract the absolute value from both sides. And because R is greater than or equal to absolute value of B, when you subtract absolute value of B from R, you still have a non-negative number. Okay? So you're subtracting absolute value of B from the right-hand side, so you got a 0. You still got this inequality. And this quantity R minus the absolute value of B, this can again be written as A minus some integer times B. Now there's a little bit of ambiguity here whether it's a +1 or a -1. This is because there's a little bit of ambiguity whether, or is there not, whether Q is a positive or a negative number. Okay. But the point is, we subtract another B's worth from both sides of the equation, and that means we've again got a number which is non-negative. Again, it's A. You can write it as A minus some multiple of B. So that means it's a candidate for the remainder. So it's a difference between A and some multiple of the number B that you're dividing. However, here you see the contradiction. Because R minus the absolute value of B, it qualifies as a member of S, because it's got the correct form for being in S, because it's A minus some integer times B. A minus some integer times B. And it is also non-negative, greater than or equal to 0. However, it also has to be strictly smaller than R. R minus absolute value B is strictly less than R. So therefore, it qualifies as a member of S, and it's strictly less than R. But hang on a minute. Just go back a few lines. R came to us as the least element of S. Whereas now we seem to be looking at an even smaller element of S. It's a contradiction. So you can't be the smallest element in S, R, and then have something smaller than you also be in S. That's a contradiction. So where did the contradiction come from? It came from this statement up here. If this were not true, if this inequality were not true. So that proof by contradiction assures us that the remainder that comes out of this is indeed strictly less than absolute value. So the remainder is unique. There's one and only one quantity r, which is non-negative, strictly less than the absolute value b, and which fits in as a remainder after dividing a by b. The other part of the uniqueness then we'd have to worry about is the quotient part unique. But once you have oh yeah, so actually the way the proof is phrased is first it's showing the existence of r, and then it's going to go on. So we now know that there's this pair of integers q and r exists because they come from the smallest element of S. I think the uniqueness is really already proved, but they just go ahead and just for completeness sake, we fully hammer it out. So if we suppose there were two pairs, a Q1R1 and a Q2R2 around, which were satisfying the requirements of integer division with remainder, well, yeah, we know that the R1 is equal to R2. That's been shown here by the uniqueness of the least element of S. If R1 is equal to R2, then when you subtract them, you get 0. But when you subtract them, you can also write the difference like this, because R1 is A minus Q1B, and R2 is A minus Q2B. So you can express their difference like this. The A's cancel out, and you've got Q1 minus Q2B equal to 0. So how can you have a product of integers equal to 0? You can only have a product of integers equal to 0 if at least one of them is 0. But all the way at the top, see, it only makes sense to do this integer division process with a non-zero number that you're dividing into the other one. So b has to be non-zero. So therefore, if we've got this product q minus q2 times b equal to 0, the only way that can be true is if q1 minus q2 is, or in other words, q1 is equal to q2. And so that gives you the uniqueness. There is only one pair, Q and R, which make this integer division process work. So the proof looks a little bit technical because it's appealing back to some of the axioms that we laid out for the integers. But it's good because it puts this process on very firm ground. So we can talk unambiguously about the procedure of taking any integer a, any other non-zero integer b, and performing integer division with remainder. And we know there's no ambiguity. We'll be referring, but if we invoke that, we know we'll be referring to a unique pair of an integer quotient q and then a remainder r. Okay. Just as an aside, in computing, certainly in Sage and probably in MATLAB as well, it's sometimes called the floor function if you want to get that q. So you can just go ahead and instruct the computer to divide a by b. That will give you some decimal number or something. But so it's normally in most computing languages that have this, it's called the floor. The floor of x is by definition the largest integer y less than or equal to x. That's the kind of integer support of x. The last integer before you get to x in the number line. Or x could be any number in the number line at all. So here's the y, here's y plus 1, and x would be somewhere in this range. Closed at the end y, open at that end. So x is somewhere in there, then the floor of x is y. Okay. Any questions about this concept of integer division with remainder? It's a useful concept to have. It allows you to, you see, if b divides a in the sense of the last lecture, then we know the remainder is 0. But if b does not divide a, well, at least this process, it allows you to capture what's going on. So we've attached a concept to the integer quotient, and we have this concept of the remainder that's left behind. So it allows you to talk about trying to do integer division of any integer by any other one, even when they don't cleanly divide. And it's also important because it'll probably be the next lecture, there's an important algorithm for calculating these greatest common divisors, which is efficient and fast. It doesn't rely on finding all the prime factors of the numbers first. It can do it very, very fast, even for extremely large integer inputs, much larger than the ones I mashed out in the page there by hitting the number keys on the keyboard. Truly gigantic integers can still find their greatest common divisors really quickly, even though you've no hope of finding the prime factorization. There's just too many possible primes that they might be. But the key step that the algorithm depends on is this integer division with remainder. And even when you have large input pairs A and B, after you've done a few of these integer divisions with remainders, you quickly get down to small numbers. Keep doing this. So if you divide A by B, and then you divide B by R, and then you divide R by the new remainder, and you keep on dividing things, and you quickly get down to small numbers. And there's a nice relationship between GCDs of all these numbers, and that allows you to get to GCDs of large numbers. So we'll be seeing that soon. So that's two reasons why this integer division with remainder is important. It allows us to talk about dividing any integer by any other one, and it's a key step in the algorithm for calculating GCDs. Okay, so you'll see Euclid's algorithms coming up on the next page. Before we get to it, we do a nice kind of, what could be called an algebraic, I've called it here a characterization of the greatest common divisor. What do we mean by characterization of the greatest common divisor? Well, we've defined the greatest common divisor as the largest number that is dividing into both of the inputs, A and B. And that's well and good as far as it goes. But here is a very, very nice result that relates it algebraically or arithmetically to the inputs A and B. So this is very nice. So what this is saying, suppose A and B are not both 0. That's just to rule out the 0 case. So A and B are a genuine pair, interesting pair of numbers. We'll let D be the greatest common divisor of them. And this theorem is saying that it is possible to write the greatest common divisor as a linear combination of A and B. An integer linear combination, meaning a linear combination of A and B where the coefficients n and m are themselves integers. Now that's really nice to have. It gives you a nice equation that tells you what D is in terms of A and B. And it relates the greatest common divisor to A and B through the operations of addition and multiplication. And it's a very useful concept that will help us along the way at many points. And a second kind of PS to this theorem, once we know that we can always write the greatest common divisor as a linear combination of the two inputs, that also tells us that any other common divisor of A and B also must divide D. We noticed that in the two examples we did, the 75 and 25, or whatever it was, 75 and 45, whatever. When we listed these common divisors, we found the greatest common divisor, but we also noticed that all the smaller common divisors all divided the greatest common divisor. We saw in those few examples, no matter what example you look at, you will observe that, and it is true in general, and this is the theorem that's going to prove it for us. And the other reason that this proof is particularly nice is that it also makes very good use of the induction principle, although using the other version of it. It makes use of the well-orderedness of the integers. The fact that any set of integers, any set of positive integers has a smallest element. So here's how the argument in the proof is really, really nice. It's really efficient and clean and neat. And it is a good example of, I mean, it's certainly not immediately obvious. The fact that you can write the greatest common divisor of two numbers as a linear combination. So what was one of the examples we looked at? We looked at, what was it, 15? I can't remember it now. Yeah, 15 was the GCD of 75 and 45. Wasn't that the one we looked at? So this theorem is saying it's should be possible to write 15 as something times 75 plus something times 45. Now if you start running through some possible coefficients, and the point is that these have to be integer coefficients. Okay, you'll soon arrive at the correct answer, sure. But you know, it's not. It doesn't leap off the page at you as a example of something that should be obviously true. Especially when the numbers start getting large, I don't think we've any intuition that tells us that this should be true. So on the one hand, it might look like something that might have a kind of mysterious proof, but it isn't really that mysterious. But it is quite a nice kind of proof that comes out of nowhere, kind of surprises you about how easy it is. Okay, before we discuss the proof, just any queries about what it is we're talking about, or any clarification about what the statement of the theorem is saying, or what it's claiming. So it's claiming that for any pair A and B, the greatest common divisor of them, which we call D, can always be written as some combination of the A and B, that is, integer linear combination, integer coefficients. Okay, so here's how the proof works. We form this set S again. It's the set of all linear combinations of A and B. So any alpha A plus beta B, where the coefficients alpha and beta are integers, and we're talking about a strictly positive value for this linear combination. Okay? So certainly this, for any pair A and B, this set is certainly non-empty. You just choose coefficients that have the same sign as A and B, so that when you multiply them, you get positive numbers, add positive numbers together, you get positive numbers. So it's S is certainly non-empty. It's an infinite set, consists of every number you can possibly write as a linear combination of A and B. So if the theorem is right, D, the greatest common divisor, should be an element of this set S. Okay. Now, D being the greatest common divisor is already kind of special. It's a significant quantity in terms of the inputs A and B. So what is the possibility? So if D is kind of special, maybe it's a special kind of element of S. And if S is just an infinite set of positive integers, what's the most obvious special element in it? But if you just know S as an infinite set of numbers, really there's only one kind of, if that's all you know about S, really there's only one element of it which is kind of special, namely the smallest element, the first element. There is no last element or the greatest element in it. It's an infinite set, and you can easily make these linear combinations larger and larger just by increasing the coefficients. So there is a special element in S, and it's the least one. And it turns out that that is the greatest common divisor that we're talking about. Okay, so how do we prove that? So by well-orderedness, S has a least element D. It's in S, so it is a linear combination of A and B. And the claim is that D is the greatest common divisor of A and B. And we prove it using proof by contradiction. If D does divide A and it does divide B, then there's nothing else. There's nothing else. So we're just trying to prove that it is a common divisor first, and then we'll establish the greatest bit later on. So it's proof by contradiction. So we suppose, for instance, on the one hand that D did not divide the number A. Okay. So if D does not divide A, then we can apply this concept of integer division with remainder. Take A and divide it by D. But because we're assuming that D does not divide A, it means we get a remainder which is strictly positive. So we're ruling out here the remainder of 0. The remainder of 0 comes out, then your B is dividing A. But if we're supposing that D does not divide A, that means we do integer division of A by D, we get a strictly positive remainder. But then we focus on, well, hang on, let's examine this remainder. You examine this remainder, it can be written as the linear combination of A and D, by taking the QD over the other side. But of course, D is already a linear combination of A and B. And by substitution, then, you quickly arrive at this expression here for R, and it shows R as a linear combination of A and B. Okay? These numbers, 1 minus Qm and minus Qn, those are certainly integers, because the Q we know to be an integer, and the M and the N we know to be integers. So hang on, that means we've got a remainder R, a quantity R, which is strictly positive, and is a linear combination of A and B. Means it's in this set S, but it also seems to simultaneously be strictly less than the smallest element in S. So that's your contradiction there. Okay. This final equation shows us that this remainder R is in S, but at the same time it's supposed to be strictly less than D. D is already the smallest element. So we've got a contradiction here, things clashing. What led to the contradiction? What led to the contradiction is us supposing this. So it isn't possible to write A as a multiple of D and a non-zero remainder, which is at the same time strictly less than D. So it must be that the only way you can do this is with the zero remainder, therefore that D does divide A. So that proves that D divides A, and by the very same method you can show that D has to divide B as well. If it didn't divide B, you can run this argument, and again you get a contradiction. But this time you'd be dividing B by B. So that's what I mean about the nice kind of move in the proof, or the kind of surprising move. You just do this little proof by contradiction here, and then we automatically know then that the smallest element in this set S is a common divisor. We know it's a linear combination of A and B, because it's coming from the set S. And then we just have to see to prove that D is in fact the greatest common divisor. Well, to do that, we supposing that E is any other common divisor of A and B, then if we go back to our Theorem 2.1, basic properties of divisibility, if we look at property 3, that was the property of divisibility of linear combinations. Just disappeared. Have I put this here? If E is any other common divisor, so E divides A and E divides B, but then D is a linear combination of A and B, so this will imply that E divides D by property 3 of Theorem 2.1. That's what property 3 of Theorem 2.1 was. If you've got any common divisor of A and B, it automatically divides any linear combination of A. So if any other common divisor of A and B divides into D, it must be that D is the greatest common divisor. One thing that's significant from this proof is it's a good example of what's known as an existence proof, as opposed to a constructive proof. So the theorem says that the greatest common divisor can always be written as a linear combination of A and B. Now you might have hoped that at the end of this it would tell you how to find the M, and the N. It might give you a method or an algorithm to find what the correct M is and what the correct N is. It doesn't do that. All it does is say that, well, somewhere out there in the ether are floating around two integer coefficients M and N that will make that equation work. That will give you the GCD when you perform that linear combination of A. So that kind of proof is called an existence proof. It only points to the existence of the quantities you're looking for, as opposed to a constructive proof, which would actually supply you with an algorithmic method, some kind of practical method for calculating the quantities that we're talking about. Okay? So it's an existence proof. We are now none the wiser. Okay, the theorem is telling us that these two numbers do exist for 75 and 45, but it doesn't give us any clue to finding them. Has anybody found them yet? What are they?
3 and 2.
Say that again? 2 and 3. First one, 2. Minus 2 and 3. So minus 150 and 3 times 45 is 135. Sorry? So 3 times 75 minus 2 times 45. Okay, you say it again clearly. 2 times 75. 2, okay, so the minus sign to the right. Okay. Yeah. Did anybody get a different pair?
Minus 1 and 2.
Minus 1. Yep. 90 minus 75. So minus 1 plus 2. Do you think they're the only 2 pairs there are, or there might be more? Why should there only be 2? It would make sense. It would kind of be in the style of mathematics if there was only 1. It was a unique pair. It'd kind of be a weird state of affairs if there was only ever 2. So the fact that there's more than 1 kind of suggests that there's an infinite number of solutions. So we'll just leave that question hanging in the air. Is there an infinite number? Can you always generate new pairs of coefficients that will give you the greatest common divisor? We'll leave that hanging in the air. Okay, I'll be seeing you again tomorrow. We'll do some associated exercises to this, and we may indeed also tackle the Euclidean algorithm as well.
Which